Hello students, welcome back to another lecture on classical mechanics and today we are having the lecture number 3a. So of course I am trying to give the numbers with a as the suffix here. The reason is that you already have the lecture numbers 1, 2, 3, etc. on the classical mechanics already on the YouTube. Okay, so already lectures are there with numbers 1, 2, 3 on the same classical mechanics, and therefore I am now giving the new numbers such as lecture number 1a, 2a, 3a, etc. And of course the important point to be noted is that I am not repeating identically same thing that I explained in the previous lecture. So nothing is repeating, so which means that lecture number 3 and 3a will not be identically same. Similarly, lecture number 1 and 1a will not be same. So that point you make sure it is going to be an additional information or with a different examples, or that the concept has been re-explained. So this is what you have to understand, rather than saying that repeating the same topic. It is there is no repeating in the series of lectures. That point you make sure. And then the entire list of video is available under the playlist. So one lecture number 1, after that 1a, then you have 2, after that 2a, then 3, after that 3a. So if you are going to follow that order, then it will be nice that the topics will be flowing in a appropriate way. Okay, so that's fine. And coming to the topic here, you can follow the green color cursor or the blue color cursor that you are seeing here. And today's objective is that we would like to know a certain important terminology in classical mechanics that we are going to use, namely what is meant by a configuration space and what is meant by a phase space. And all these kinds of phases are generally comes under a single heading, what is known as mathematical space. But already you have something called a physical space. Physical space you already know. It is the space in which you are currently living, or all the physical objects exist. So that is the physical space. And in addition, you also have something called Euclidean space. So why so much of terminology? Why so many names are there? And how do I understand at present, for the time being, for classical mechanics, we need to have a clear understanding of the configuration space and the phase space. So today's lecture is on this topic to clarify the meaning of each one of the space, and in particular, given the configuration space, what is that you are going to do, and how different is the configuration space when compared to phase space. And of course, all these things should be connected with the physical space, because that is the space in which you are going to live, and that is the space in which you are performing the experiments. So ultimately, everything should be connected to the physical space. So that is the idea. And then the connection, of course, comes naturally. And for giving the connection, we need additional terminology, what is known as constraint of the system and the degrees of freedom. So these are additional terms are coming so that you can make the connectivity between the physical space and mathematical space. If you don't have constraint, if you don't have degrees of freedom, if you don't have such kind of concept of doing the calculation, then we will be unable to make the appropriate mathematical connectivity between the physical space on one side and mathematical space on the other. So that connection comes through what is known as the degrees of freedom, and the calculation of the degrees of freedom requires the constraint. Constraint, we will be using the constraint is the terminology. Of course, you already know that constraint means a restriction or some kind of compelling movement. Okay, you are forcing the movement to happen in a particular way. So that's all about it. And but however, we will now use the word constraint only, not equivalent terms. Okay, so let us therefore continue with today's example. I'll be showing in the board the distinction between a one particle system or a multi-particle system, how the connection goes. Okay, let us go to the board and I'll explain that. To two classes, and especially we were discussing about the how to understand the generalized coordinates from the usual notations like x comma y comma z. And there is a point to be noted. Of course, when that point I will explain. So in the last of two classes when we are discussing, we were talking about the different coordinate systems and then making transformation from the Cartesian system to the uh, to the spherical polar system or any other coordinate system. It can be anything. 11 of them are very common and very familiar, as I already told you. But other than the 11 coordinate systems, it is possible to have different arbitrary coordinate system. It's possible. So ultimately, the point that we were discussing, or that the point that I was telling in the last class, is that we can make a coordinate transformation from Cartesian to spherical, spherical to cylindrical, cylindrical to hyperbolic coordinate system, or hyperbolic to elliptical coordinate system, or we can come back from elliptical coordinate system to Cartesian. We can make any of the transformation. Now each one of this transformation is what is known as the coordinate transformation. And there are some underlying features are there in coordinate transformation, namely that the Jacobian of the coordinate transformation should not be 0. So I will not right now enter into what is the meaning of Jacobian of coordinate transformation. It is actually a determinant containing the partial derivatives. So if the Jacobian is 0, then coordinate transformation will fail. That's the meaning. So essentially, you can easily understand very simple thing like x comma y going to the r comma theta. X comma y going to the r comma theta. That itself is the simplest coordinate transformation. And if you calculate the Jacobian, it will not be 0. So Jacobian calculation is very simple. You only have to evaluate the partial derivatives like dou x by dou r, dou x by dou theta, dou y by dou r, dou y by dou theta. Because xy is there on the left side, r theta is on the other side. So you calculate all possible partial derivatives and evaluate the Jacobian of that. Jacobian is nothing but a 2 by 2 matrix, I mean 2 by 2 determinant, because it is a 2D system. If it is a 3-dimensional coordinate system, then it will be a 3 by 3 determinant. So there is an underlying feature that is very important, that the coordinate transformation, when you are talking about the mathematical coordinate transformation, it is implied. It is implied means classical mechanics doesn't enter into picture for the transformation. It is originally it is mathematics actually. So mathematics guarantees that the coordinate transformations are successful. That means the Jacobian is not equal to 0, and therefore it is possible to move from one coordinate system to the other and then come back to the original system. That is called the inverse transformation. So these points should be remembered, and there is nothing to do with the classical mechanics. So classical mechanics doesn't say that the Jacobian should not be equal to 0. So that kind of condition doesn't come from mechanics. It is a condition that already exists in mathematics, namely the coordinate transformation, and the same concept will be used here also. So at the end of the last class, if you remember what is that we have written in the end of the last class, we have said, or we have written an explicit terminology saying that it is the transformation of the coordinates. So when you are talking about the transformation of the coordinate, you should remember what I explained right now, namely that the Jacobian of the coordinate transformation should not be equal to 0. That is one thing. There is some special case that, let us not worry. There is a special case saying that if the Jacobian is exactly equal to 1, identically equal to 1, then it is a special case, what is known as the flow will be preserved. Or we say volume, exactly if you are talking about, it is the volume preserving coordinate transformation. So right now, no need to worry about that, but just remember that Jacobian is exactly equal to 1 is something special, which will be useful in classical mechanics. And of course, it will not be 0 at any time. In case if it is 0, then the total thing will fail. Okay, keep that point in mind when we are talking about the transformation of the coordinates. And let us now come back to in the today's class discussion, where we will see what is the connection between the physical space. Physical space is the space in which you are living. And then you already know what is an Euclidean space, and then we are talking about mathematical space. So we are particular about two terminology. Okay, that means one of the terminology frequently used is known as the configuration space. Another terminology or term is the physical, that is the phase space. So you see different terminologies are coming. Physical space, Euclidean space, then you have a configuration space, then you have a phase space. Like that, many names will be coming. These names are what is known as the terminology. And when the terms are clear to you, then classical mechanics will be looking simple. If the terms are not clear to you, or if you are unable to use a particular symbol for the respective phases, then the classical mechanics will look as if it is a very difficult topic. So that is why I am spending considerable amount of time in explaining the basics more. Once you understand the fundamentals, then moving to the next topics will be quite easier, and you can also do it little fast also. So let us therefore come to this particular case, and you can follow the cursor here, blue color cursor, and we will see an example of the one particle system where we can write down anything like this. But for that I would like to show a small video. Let us consider some kind of a bird flying, for example. So here you can see that a bird is flying. Let us understand how it is making its dynamics. It is trying to maintain some constant height, and it is trying to make some kind of circular path, and that's all about it. So that's a small video, and that will give you an idea about a dynamical system. So we ask the question, first of all, the terminology is the dynamical system. It will be frequently used, of course. All the time you will be using the word dynamical system. So the word is, what is a system there? System is anything that you want to study. So in the example that we have seen in the video, a single bird is flying in the 3 dimension. Of course, it is just flying in the physical space. So our system that we are writing, so here I am writing, that's why you have to be careful. The word system is written here. What is a system here is that what is the object that you are studying is the system. It may be a single particle system or a multi-particle system, or it could be several particles with some connections in between them. Connection means physically you can connect one to the other using some kind of rod, chain, anything you can do, right? So all of them are dynamical system. So we will understand what is a dynamical system. A dynamical system is a system that makes temporal evolution with respect to its time. So if time changes, the system also will change, or it will not stay at a particular place. It may be making rotational dynamics, it may be making translatory dynamics, or a combination of them. So anything can be there. Okay, pure rotation is also allowed, pure translation is allowed, a combination of rotation with translation, anything is okay. As long as it is not static, we say it is dynamics. And the system can be a single particle system, multi-particle system, etc. Now to start with, for the easy understanding, we will consider a single particle system right now. That's what I have written here. And as you can see that I am writing x, y, z is the 3 coordinates. That means if you want to locate means if you want to find out the coordinates of the location of the bird at a particular time, because it is constantly moving, right? You cannot find the coordinates as it is moving. So you have to take a photograph of the flying bird. That is called a snapshot. Once you take the snapshot, the bird will not be moving there. It will be stationary. Under that condition, you can measure the location, what is the x value, y value and z value for a given coordinate system. So remember that if you want to find the location, the xyz coordinate system has to be first of all brought and fixed at a particular place. If you don't have this kind of a, I am showing here in blue color coordinate system, that coordinate system should be somewhere fixed. That is what we say laboratory frame of reference. Laboratory frame of reference means frame of reference is called coordinate system. Mathematicians use the word coordinate system. Physicists use the word frame of reference. Both are same. So the coordinate system or the laboratory frame of reference should be first of all identified. Now once you identify, then we can correspondingly write down x, y, z depending on Cartesian, rho, phi, z if it is cylindrical, or r, theta, phi if it is 3D spherical system. So which means that what you understand from here is that we are having a single particle. There is a numbers, you have to be careful about the numbers here. It's a one particle system, single particle. That is, we are considering particle as a bird. We will not consider for the time being a bird is something like a larger body. Okay, there is a difference between the word particle, and then later we will talk about some rigid body. The distinction comes in terms of size and shape. Particle, here this is important. Particle means we are going to make an assumption that it is too small, that when the object is too small, you assume that it is spherical in shape, even though it is not implied. It is not explicitly written that particle will be spherical in shape because it is too small, like an electron, for example. We don't say that electron will be triangular shape. prism shape. We don't say like that. Electron is too small, and therefore we will assume that it is spherical in shape. When something is too small, we don't bring its shape into consideration. And in mechanics, what is the meaning is that you don't bring into the concept of moment of inertia. That will not come into picture. So when you are talking about the mechanics of a single particle, we will not discuss anything on the moment of inertia. But if you are going to bring the concept of a rigid body, okay, that means something like a blackboard or something like a microphone, anything like a water bottle, anything like that you bring, then we will bring the concept of the shape of the body. Once you have the shape of the body, and because of the extended size, then naturally the concept of the moment of inertia comes into picture because of its possible rotations. So this distinction should be clear here. So when we are making the terminology particle here, it is understanding that the particle means that it is too small, that you don't have to bring it into the shape into picture. And that is a point that you are going to remember and understand as we move along. Okay, here I have written one particle, that means one number is there, but here we have written x comma y comma 3. 3 is there. So there is a one particle is there, but 3 coordinates are there. So the number 1 and 3 is there, right? That is the connection that you should now pay attention and then understand. So what we are trying to say finally, what is that we are trying to say is that the configuration of the system, so here I have written the word configuration is the word that we are going to use. The configuration of the system, in our case it is a single particle system, is written using the generalized coordinate notation by the symbol qi. And the important point is that the I equal to 1 to 3 has to be written down explicitly. It has to be written down. If you think that I equal to 1 to 3 is not important and no need to write that, then it is totally out. That means you are missing a huge information, very important information. I equal to 1 comma 2 comma 3 means 3-dimensional. I equal to 1 comma 2 means 2-dimensional. I equal to 1 only means 1-dimensional. So therefore, how important is that you should remember whether the dynamics is taking place in 3D or the dynamics is taking place in 1 dimension. That should be clearly written. Otherwise, total physics will be lost. So therefore, writing down the suffix I equal to 1 comma 2 comma 3 is very important, and it has to be maintained as we go along. Okay, so this is how you write down, okay, configuration for a single particle system, you write like this. And in the example video that we considered where the bird is flying, we also make a understanding or note that there is no constraint. So we don't tie the bird with a thread or rope, and in that way the bird will be unable to fly. We didn't make such a thing. So that means the bird is allowed to fly as freely as possible, which means that nature has given 3-dimensional space, and therefore the bird has the ability to travel in the x direction or in the y direction or in the z direction, or simultaneously a combination of all the three. That's what we have seen. When the bird is flying, you can see that its height is slightly going up and down. It is also making translatory xy direction. So therefore, we also make an important note about the constraint in the system. Now these two things are very important in order to calculate what is known as the degrees of freedom. Because calculation of the degrees of freedom is very important, and of course in the competitive examination such as the NET examination or the GATE examination, many of the times they will ask you what is the number of degrees of freedom for a given problem. They will give you a simple problem and they will ask you to find out what is the degrees of freedom. It's a small number that you have to find out, and calculation of the number requires these numbers, like one particle means 1, 3 coordinates means 3, and the constraint calculation we need it. So that is why I am taking some time and explaining here. And now let us understand better. Now that you have seen the video of the bird flying, and if you want to represent the that particular dynamical system of the bird in a configuration space, how it looks like, that's what I am trying to show here, so that you can feel what is the meaning of configuration space. I am trying to explain you what is the meaning of configuration space. Now I have put a yellow color dot here and then writing 1 here. What is the meaning is that at an instant, at a particular time t1, let us say it is a time t1, at that particular time I take the photograph of the flying bird. Now once you take the photograph, that in that photograph the bird will not be flying, it will be stationary, and therefore I will be able to find out its x comma y comma z location and then put a dot there. That is the yellow color dot. Similarly, after some time I will take one more photograph. After some time I will take one more photograph. So at time t2, at time t3, at time t4, etc. So therefore at different times I can take the photographs, and just in this particular case it appears as if the bird is making some kind of circular motion, and that's why I'm typically representing like that. So it need not be circular and come back here, it can go anywhere. Okay, so the idea is that what you understand is that the configuration space means it is the set of numbers that you are going to have, and then you can show it on a graph, and if you show that, then it is known as the configuration space. Space means mathematical space. Now comes a very important point. I will tell you the distinction. Of course, before that I want to tell here, because I have written a conclusion here. The conclusion is that the configuration Qi is called configuration. Remember that. Qi means configuration, because I have written here, right? You must be able to see that. Here I have written, see, configuration Qi. So that word you have to remember. So once you remember, so now you have, I have written like this. So the configuration Qi is now a function of time. As you can see that point number 1 is one configuration, point number 2 is another configuration, point number 3 is another configuration. Configuration means instantaneous snapshot of a dynamical system. That's all. That is the meaning of configuration. So therefore, configuration will be a function of time here. So what you understand from here is that the diagram that we have shown here, namely this whatever diagram that you have, does not contain the information about the time. So it has some negative points. I mean disadvantage. What disadvantage you have from this configuration space is the information about the time is missing. That is first point. Second point is you don't know what is the speed of the bird. At different times the bird may not be flying at the same speed at all the time, right? The bird may be flying at higher speed, lower speed, etc. You don't have the information about the speed of the dynamical system. In our case, the dynamical system is a single bird. So the information about the speed is completely not there in configuration space. Okay, so that is a point you remember, and then we will move ahead and then discuss about how to make the inclusion of the speed. Okay, so here, before going to the further explanation, I would like to make an important distinction. This distinction is quite important. What is the important is that you have a physical object. Physical object can be an airplane or a cricket ball or the bird. Anything is okay. Anything is a physical object. Where is the object present? The object is always present in the three-dimensional physical space, because it is the space in which you are living. It is the space that you are seeing in everyday life, and the physical space is always three-dimensional. You may be putting the restriction and making it one-dimensional. So that is only because of the restriction it comes. If you don't put any kind of restriction, then nature provides you three-dimensional space. And that space is what is known as the physical space. So physical space in which physical objects exist, like in human being is existing, means space is given to them. If space is not given to, if no space is given, then a particular object cannot exist. Whether it is living object or non-living object, it doesn't matter. No object can exist if you don't give any space. Okay, I don't give any space means what? 1 millimeter cube, 1 centimeter cube. That is the space that you have. I will not give any space. Then how a chalk piece can exist? So you know that chalk piece has some length. It has a small diameter, like 1 centimeter diameter. How the chalk piece can exist? It cannot exist if you don't give the space. So the point to be noted is that only if the physical space is present, you can have a physical object. This is one concept. Keep it this side. You come to the other side. On the other side, what happens is, in order to understand the physics, okay, now mechanics we are talking about. Okay, in order to understand physics, in order to understand mechanics for the time being, we need mathematics. If mathematics is not there, we can't understand physics. And therefore, what happens is, you bring the concepts of the mathematics now. The first one concept in the mathematics is the mathematical point. It is also known as coordinate. Coordinate is different, coordinate system is different. Coordinate system means a set of x, y, z axis, a set of r, theta, phi axis. You need 3 perpendicular axes there. That is why it is called orthogonal coordinate system. Orthogonal means perpendicular. X and Y perpendicular, Y and Z perpendicular. Similarly, R and theta perpendicular, theta and phi perpendicular. Everything is perpendicular. That is why it is known as orthogonal coordinate system. We will not discuss about non-orthogonal for the time being. We will not discuss in this course, but it is possible to have. So, coming to this, orthogonal coordinate system is one. Forget about system. Only coordinate. What is it? Only coordinate is, that is a point. So, mathematical point is only a coordinate. That means a set of numbers. Now, this should be distinguished. Distinguished means this is different from the physical object that is located there. So, this concept is very important. And now, in order to see the distinction, I will draw a small diagram with a coordinate axis, then it will be clear. So, here what do you see? We are considering a simple 2-dimensional case. So, if you draw the x-axis and if you draw the y-axis and with an origin there, that is called coordinate system. Blue color one. So, this blue color one. Okay, that is over. Then come to the white color dot here. With a white color dot, and I have written some numbers 3, 2. Of course, you can measure from the origin. This is origin. So, that will be a 1, 2, 3, etc. That's why 3 is there. And they said you have 1, 2 and therefore 2 is there. So, you already know what is this 3, 2. So, 3, 2 represent a point in the coordinate system. That is very clear to you. There is no doubt about that. But what is the point that I am emphasizing is, the point is physical point or mathematical point. That is what I am trying to explain. Everyone knows that 3, 2 is a point in the coordinate system. But the clarity that you should now have is 3, 2 is not a physical point. It is not a physical object. It is completely a mathematical object. And the mathematical object is known as mathematical point, or you say geometrical point. Now that distinction will come, it will be much more clear if you can imagine what is the size of the object. Now, I have put a white color dot here, right? Here it is there, white color dot. And I am saying that it is a geometrical point. Now you ask the question, what is the size of the geometrical point? Can you take a vernier caliper or a screw gauge and measure what is the size of this particular 3, 2 point? The 3, 2 is a point, right, in the coordinate system. What is the size? Can you say that just 1 millimeter, or it is much smaller? Can you say that something like 1 millimeter or smaller than that? 1 micrometer may be very small. So, if you ask that question, then the clear distinction will come. Clear distinction will come. The answer is this. Geometrical point is a point whose size is exactly 0. Identically 0. Okay. There is no micrometer. There is no nanometer. It's identically 0. That means mathematical point doesn't occupy any space. It doesn't require a physical space to occupy. It is a concept. That is why we bring the name concept here. Concept of mathematical point. We don't say the concept of physical point. Physical point means something that you can see directly. For example, cricket ball. Cricket ball is a physical point. You can bring the cricket ball and keep it at the location 3, 2. That is visible to you. If it is not visible, maybe you can see through a microscope. That's all about it. So, physical objects and mathematical point or geometrical point are two different things. These two things are not the same. And therefore, the concept that we are saying is that now the bird is located at the point 3, 2, or cricket ball is located at the point 3, 2. Like that we have to tell. Which means there are two things are there. One is the geometrical point and the other one is the physical object. So that distinction should be clear. And whenever there is a physical object, that is located in physical space. Whenever there is a mathematical object like this 3, 2, that is located in mathematical space. So now I am trying to explain the clear difference or the clear distinction between physical space on one side and mathematical space on the other. So don't confuse the terms space, because space is there everywhere. You should not think that space means physical space. It has to be a clear distinction. Okay, I will try to give one more example. It will be much more easier to understand. Now you are having the number 3, right? You have a number 3, you have a number 2. 1, 2, 3, 4 is there, right, in mathematics. You ask the question, okay, what is the proof that number 3 is there? Can you show me where the number 3 is living? Living means existing. Okay, you have to show, you show me the finger and tell me where is the number 3. So that I can now see that, okay, number 3 exists in the world. So the point is that you can't show your finger and say that this is the place where the number 3 exists. You can't say that, okay, see the cursor now, blue color cursor, no, this is the 3, like that you cannot show, because that 3 is, I have written it in a physical space. That is not the real 3. I have written it in some physical space. I have written. That is what you are seeing. That is not number 3. So this is not a simple thing. You have to be very careful in understanding, and it requires imagination power. So ultimately the point is that numbers like 1, 2, 3, real numbers like all fraction of 1.1, 3.14, all kind of these kind of numbers, everything exists. If it exists means where it is existing. Existing means living. Where it is existing means they all live in mathematical space. Or we say that mathematical objects exist in mathematical space. So geometrical point is a mathematical object, and therefore it exists in mathematical space. So that is one side of the story. Another side of the story is we are bringing the concept of the mathematical object and then keeping the physical object there for our calculation. So that is the connection that you are going to give. This connection is very important because several times means not only in classical mechanics, next in quantum mechanics you are going to see another variety of space. So all the time some kind of space will come. So there will be a big confusion why so many spaces are there, and in what way the physical space is different. So now it is clear that we can describe numbers in different ways, and each one is a mathematical space. So let me therefore give the clear understanding now for the generalization. Now we are going to start with the specific single example. Now what is the single example that you are having is, one second. Okay, so what is the example that we have is, in the case of a single particle system, we have xyz, and that has been generalized and written as q1, q2, q3. That is clear to you. Now I am asking you to focus your attention on the number of particles in the system and the number of q's here. How many number of q's are there? q1, q2, q3. 3 q's are there. How many particles are there? Single particle system. Only one bird is flying. So if one bird is flying, I need 3 q's. So that point you remember, and if it is the case, this number is what is therefore known as dimensionality of the space. You see the number is coming here. That q1, q2, q3, 3 numbers are there, 3 q's are there, therefore 3-dimensional. Suppose I want to extend this concept to over and above 3, then suppose if you write q1, q2, q10, I will call that as 10-dimensional space. Okay, why only 10? 10 can become 5,000, 5,000 can become 1 million. Any number is okay. So in that case, we will be writing like this, q1, q2, like this, q1, q2, q3 up to qn, where n can be anything depending on problem to problem. So n is going to be an integer number. Okay, so n cannot be 1.5. You can't stop at 1.5. Okay, 1, 2, 3, etc. So that's all. Therefore, n has to be an integer there. And now if you are going to say that, then it is known as n-dimensional space. So once you talk about this kind of numbers where you have more elements are there, you have to naturally understand that we are talking about the mathematical space. So the point that I would like to tell you is that the moment you are talking about something higher number like more than 3, you have to clearly understand that it is mathematical space. So you should not confuse that how can you visualize, how can I see 10 dimension, how can I see 20 dimension, means there is nothing to see and you can't see also. So don't, if it is difficult to see, then you can say, okay, let it be difficult, I will try. It's not possible to see, so why do you want to struggle? That's what I am trying to say. You cannot see a geometrical point, single point you can't see, and how can you visualize 10 dimension? So the point is that all this mathematical set of variables, so it's only as simple as this, it is a set of q's, that's all. So let there be 1 million q's. It's one set, and that's a mathematical object. We say that it's a mathematical object, and this is what is known as configuration. So now you understand what is a configuration space. Configuration space is a mathematical space in which we put that many number of q's. Q means what? Location. Q means position. Position, that's all. At what position, at what location a particular physical object is existing at a particular time. Remember, particular time. If time changes, all q's also will change. So q1 comma q2 comma q3 is valid only at a particular time, instantaneous time. If the time changes to a small value, then the q1, q2, q3 also will change. That is why dynamics is taking place. Okay, so this point is clear. So once this is clear, now let us therefore understand one more thing. I want to at least tell you what are the different names of the mathematical space that you will encounter in physics. The one which is familiar, I will write down the first one, namely the three-dimensional Euclidean space. And of course, here I would like to explain that the three-dimensional Euclidean space is the corresponding mathematical space of the physical space. It is direct one-to-one correspondence. You have x-axis, so that is what is represented in the Euclidean. So remember, three-dimensional Euclidean space is the equivalent of the three-dimensional physical space. It is exactly mappable. One-to-one mapping can be done. So that is why it is a three-dimensional Euclidean. But mathematically speaking, there is no compulsion that you have to stop at 3. You can go to 4D, 5D, 6D, 100D, whatever it is possible. So we say n-dimensional Euclidean space. The moment you go above 3, then there is no physical correspondence. So you should not compare anything with the physical space. So don't worry about anything, and it is only a set of n numbers because small n is there, right? N-dimensional Euclidean space. Okay, this is one thing that that is quite clear and easy to understand. And of course, as this point I already explained in the last class, namely in the case of the 4-dimension, you remember one more point. 4-dimension, 2 varieties are available. 4-dimensional Euclidean space, yes, it is available. 4-dimensional Minkowski space, that is also available. But these two are not same. This is very important. 4-dimensional Euclidean space is not the same as 4-dimensional Minkowski space. These two are very different. Of course, the reason for difference I will tell right now, but not right now, no need to worry. The main difference is that in the case of the 4-dimensional Euclidean space, all the elements will be of the form space. Space means if you are going to consider 1 meter, for example, similarly second element will be in meters, third element will be in meters, fourth element will also be in meters. We are talking about distance. In the case of the Minkowski space, it is not that. First 3 of them, okay, it depends on whether you write first 3 or last 3. Okay, first 3 of them will be space. Meter, meter, meter. The last one, that is the fourth element, will be in time, right? Seconds. So meter, comma, meter, comma, meter, comma, second. Okay, that is called x, comma, y, comma, z, comma, t. So these two spaces are very different. Of course, both are mathematical space only. These two mathematical space are completely different. So they are not at all similar. And of course, the question comes, now what do you mean by different mathematical space? The answer is, mathematical space is characterized by their own mathematical properties, what is known as geometric properties. This is very important. Geometric properties. What do you mean by geometric property? Means finding the distance between 2 points, because that is the one that is quite familiar to you. In the case of the 3-dimensional Euclidean space, you know how to calculate the distance between 2 points. Square root of x1 minus x2 whole square plus etc. So it is one property. Like that, many properties are there. So if you are going to list out what are the geometrical properties for a particular space, then you have one list. On the other side, you take another space like Minkowski space and then write down their properties. Then what you understand is the properties that are listed out on the left side and the properties that are listed out on the right side will be very, very different. And because of this reason, we say that one mathematical space is very different from other mathematical space. Because of this reason, you have several mathematical space. Now you understand why several of them are there. Several of them are there because the properties keep on changing. If you have a different set of properties, it means you have discovered a new mathematical space. That's the meaning. And if it is the case, now I will write down at least a few of them, which is very important, especially for, say, quantum mechanics. In quantum mechanics, you will be using the so-called Hilbert space. So Hilbert space is, what is that Hilbert space is? Once again, it's also a mathematical space, but its elements are very different. Okay, you won't have real numbers. And similarly, you can have a topological space, Banach space. Several spaces are there. Okay, some numbers, I don't want to write a big list. A few of them for understanding purpose. Now in this, the Hilbert space is of course a very important one that you are going to study in quantum mechanics, where we say that number of dimension is infinity. Because this point I am writing here because we are talking about 2-dimensional. 3-dimensional. I said that n-dimensional is possible, but when n itself goes to infinity, even then it is possible that, as an example of the infinite dimensional space, is what is known as Hilbert space. Hilbert space is nothing but the elements will have complex vectors, that's all, complex valued vector functions. Remember one thing, that in the case of the Euclidean space, when you write numbers like 2, 3, 4, 2, 3, 4 is x, y, z. These numbers are real numbers. So 3D Euclidean space, set of all real numbers. N-dimensional Euclidean space, each one of the element is a real number. Complex number will not come. Similarly, in the case of the 4-dimensional Minkowski space, all elements are real. X, Y, Z space, right? So many meters, real number. And last one is time. How many seconds? Real number. So these are all real numbers. But in the case of the Hilbert space, everything goes to complex valued, and it is not a number itself, it becomes a function instead of a simple number. So complex valued functions will be the elements of that particular mathematical space. And we will not worry right now. When we go to quantum mechanics, we will see that. Now it is very clear. Of course, topological space and other things will be using when you are going to the general relativity. Banach space much we will not use, but sometimes it is useful for understanding quantum mechanics. So like this, there are a big list is there. I am not writing many of them, but this is enough. Now it is clear that whenever you see the term space there is nothing to worry about. And coming to the classical mechanics, I would like to write down that we are talking about the phase space, and there is another name for that, what is known as the state space. Two names are there. Phase space is the most frequently used. I will put a tick there. So phase space is frequently used. State space only some people use it. That's all about it. And so the idea is that the important point is that we are talking about in the classical mechanics the configuration space and the phase space. So now you understand why the names are coming there, and then how different it is means how different depends on the properties and dimensionality. That's all. So right now, for the case of the classical mechanics, we need the concept of the n-dimensional real space, what is known as configuration space, and also we need the concept of the phase space, which is nothing but double this number. So remember, if the configuration space number is n, then the phase space dimensionality will be double of that. If this is n means that is 2n. If this is 100 means that will be 200. That's all. The doubling will be there. And of course, why doubling is happening is you already know that velocity is missing, right? Speed of the bird is missing. Okay, I think the names are not visible. 1 second. Okay, so these things are now visible. You can now see. Okay, so the point is that how this is doubling is taking place. N to 2n is that speed. I said that the speed of the bird is completely absent in configuration space. So we don't want to lose that knowledge. Okay, only the speed is the one that is going to talk about dynamics, right? So we have to bring the speed of the bird or the speed of the particle in our calculation. So if you bring that, it becomes double. That is position comma speed. Position comma speed means position alone is configuration. Position with the speed is phase space. So now you understand why it is doubling, because two quantities are there. Okay, so that is clear. Okay, so I think almost now we are understanding in a better way. And now I would like to explain with a much more clear example here for the configuration space and the phase space here. I'll write down, then I'll explain. So these are the many of the things that I already explained. Okay, so that's all. So now, of course, you now understand what is the overall idea. Whatever we discussed, now it is there in single place. Configuration space means set of all Q. That's all. Remember like this, set of all Q. How many number is very important. That number has to be calculated correctly. Otherwise, it is totally it will be wrong. So n is required here, and that is what is the point to be noted, that the number n has to be clearly identified, whether it is 3 or 6 or 21, whatever be the number. And the configuration space is just a set of Qs, and this is equivalent to a snapshot of a dynamical system taken at a particular time. Remember, some time means I have written particular time. And now if you are going to compare and contrast with the phase space, now you see that the information about the speed, or we say velocity, at that particular location is what is also included. For Q1, you write down, how do you understand? This has to be understood clearly. When the bird is located, we are talking about bird, right? When the bird is flying and when it is located at the point Q1, it was flying at the speed Q1 dot. That is the meaning. And when the bird moves to a different location Q2, it was flying at the speed Q2. And similarly, when I am taking the snapshot at the nth time, then it was the bird was located at Qn. At that time, the speed was Qn dot. So now you understand the entire list that you are going to have. And of course, the n, you can understand the later n. I'll explain how to understand the n here. That point I will tell. But before further moving, we are not going to write q dot, q dot, q dot. So instead of writing like that, it is traditional to collect all q's first and then write all the dots next. So now you see that all q's are written first of all, and dots are written at the end. So now it is clear that it is the set of generalized coordinates together with the set of generalized velocities. So these terminologies are important. Now clear distinction is coming between the phase space and the configuration space, and some more important points are there. I'll explain, I think, before closing the today's class, because this number has to be explained clearly. I'm talking about the number, okay, dimensionality. So here I'm highlighting because these are important here. I am talking about how to know n here. That n, how to calculate, that is very important. If you know how to calculate n, then it is a matter of doubling it. So making doubling is very easy. First of all, this n should be clearly identified, and then we can do this. And this point you remember, when we write the set here, first of all list out all q's. Afterwards list all the velocities. Like that you write, not like this. Position velocity, position velocity, position velocity. Not like that. Set of all position, comma, their corresponding velocity. Corresponding is important. Their corresponding velocity, not some random velocities you are writing. Okay, so that point is important. And once this is clear, and let us now go to an example and then understand how to find, or how to understand what is this number exactly, how to calculate that. So I'll take an example and explain for that. Okay, so for doing the calculation, we will consider some symbols here. Of course, we will consider n and capital N. Here this is very important. Whether you are going to use capital N, small n, or some other symbol, it's all okay. But I am going to use small n for one meaning. Capital N is a different meaning. So small n and capital N are not at all same. They are different. So that point, let us make sure that we don't mix them together. And we will also understand like this. Small n means number of particles in the system. Capital N means dimensionality of the mathematical space. That's the meaning, dimensionality of the mathematical space. You can also interchange and use it. That's not the problem, but you have to be careful which is the one representing number of particles, which is the one representing dimensionality. It doesn't matter. Small n can be dimensionality, capital N can be number of particles. That's not a problem. Anything is okay. But let us fix one thing and then work out. Now, why I am telling like this is, from one book to another book, when you read, we do not know which author will use small n for number of particles and capital N for number of particles. Somebody will interchange. So interchanging is all fine. But you should be clear what we are doing, and similarly you can calculate if the symbols are changed. But there is one important point. The dimensionality of the mathematical space, remember, dimensionality of the mathematical space, now in particular configuration space, is what is known as the number of degrees of freedom for a physical system. Now, these two things you have to be careful, that the one which I have written in the first one, namely the dimensionality of the configuration space, is the technical term used by mathematicians. But physicists use an equivalent term. So these two are equivalent. And physicists, what they use is degrees of freedom of physical system. So when the two terminologies are coming like this, you should not think that okay, something different thing is going on, and as if it is complicated. So that point should be clear. So we are talking about the same thing, whether you can use this word or that word. That's why I am using the word frequently, terminology. Terminology means what kind of terms are frequently used by mathematicians and physicists. And we'll have to use interchangeability, because we are anyway taking the help of mathematics to understand physics, right? So naturally we need to learn both the terminology of the mathematics and the terminology used in physics. Okay, let us keep this point very clearly, capital N and small n. If you interchange and mix and get confusion, then all calculation is wrong. Okay, fine. Now take the example. In our case, we have taken an example of a single bird, right? We can consider a single bird, I'll write down as a single particle here. Now you can easily understand how to write down these numbers. Okay, so this is an example. Okay, forget about the bird problem because I have drawn here. Let me explain about this, and we'll go that later. We are going to consider a single particle. It can be a single person walking on the road, or that some kind of ant that is moving on a particular line. So it is only allowed to move on a line. Okay, if a person is there, he is allowed to move only on the road. Okay, he may not be able to go that side or this side. Like, walking on the rope. People who are walking on the rope, you can't move to the left side or right side, you'll fall down. So you are compelled. So you remember the word compelled is coming here. You are compelled to move on a particular line. So keep that as an example, and because that's very important, I'm going to write down the constraint here. This constraint has to be written once you understand the problem. So if you see now what is the meaning is, if a person is walking on the rope, then the rope becomes the x-axis. I have written the x-axis here, right? So you have to consider that the rope is the x-axis. And if you are asking about what are the constraints, because in the yesterday's class I told you, holonomic constraint, non-holonomic, etc. You have to write down a mathematical equation. Simply saying constraint, that will not work. Equation has to come. So what kind of equation do you want to write means, when you say that a particular particle is allowed only in x direction, means it is not allowed in y direction, it is not allowed in z direction. Now how do you rewrite this English sentence to mathematics? That's what I have written, y equal to 0, z equal to 0. Now how do you know that y equal to 0, z equal to 0? How do you know that? That is, in the sense, how do you know is that we will have to bring the y-axis and the z-axis in our diagram. That's what I am doing here. Now you see that. Now try to bring the y-axis and the z-axis in our coordinate system, and then the person who is walking would be the particle. We can represent it like a particle. Now you understand that when the particular particle is traveling only along the x-axis, what is the value for y? The value of the y will be 0 all the time. So that is what I mean to say. All the time is very important, not instantaneous. If it is instantaneous, means you are out. That is, constraints cannot be instantaneous. This is very important concept. When you are talking about the constraint has to be constraint all the time. All the time means until the dynamics is completed. If you are studying simple pendulum, if there is a constraint in the simple pendulum, that constraint should be there all the time until you finish the experiment. Then only all the calculation is correct. While doing the experiment, if the constraint itself disappears, then whatever you are writing is totally wrong. So that is important. So the constraint should be all the time valid. That is why, remember once again, that is why some people will use the word kinematic constraint. Kinematic means as the kinetics takes place. That means kinetic means something changes with respect to time, right? That is the meaning. So kinematic constraint will be the word that will be used instead of saying constraint. It is a kind of adjective that you use in order to emphasize that the constraint is valid all the time till you complete the experiment or experimental observation. That is the meaning. Okay, so y equal to 0 is valid until the dynamics is studied, and not only that, okay, not only that, and the value of the z is also equal to 0 when the person is walking along the rope. That means he cannot jump in the sky and come to this particular position. It's not allowed, that's the meaning. So now that you have written two equations, it's very nice. Now English sentences are converted to mathematical equation. Now you can tell whether these are equality relations or not. These are equality relations, so very good. But equality relation is not the only requirement. In addition to that, very important condition is it should be solvable. If there is a trouble and if there is an unknown, and if I don't know what is the value of the unknown, then what is the use of the equality relation? Equality relation becomes useless. And that is what we say non-solvable. When it is non-solvable equation, then it is a trouble to us. And whenever there is a trouble coming, you say that it is non-holonomic. Non-holonomic means a problem that is not solvable. Now in this case, any trouble is there, you have to tell. Y equal to 0, okay, I always know the value of y because I fixed the coordinate system. So there is nothing is unknown here. Everything is known. Equality relation. So equality is also guaranteed. Unknown is also eliminated. There is no trouble now. And therefore, we will classify the set of two equations that you have written down as holonomic constraint. So I'll write down that. I'll finish some writing, then explain. Okay, we are calculating dyf. Dyf means degrees of freedom. Okay, this is the equation that's very important. So that's why I'm writing the entire thing. Okay, let it be there. Maybe I'll just go to the previous line. I want to explain the previous line and then come to this. I think it has gone little above. So okay, I was talking about the holonomic constraint, right? So I want to tell that holonomic constraint, we will represent it by some symbol. Any symbol is okay. We will use C for the constraint, and this number has to be carefully written down, because I said that in the competitive examination a small problem will come where you'll be asked to calculate the degrees of freedom. To calculate the degrees of freedom, the number C is very important. So it is not that people make mistake in calculating degrees of freedom. It is the place where people make mistake in calculating the C value. C value means number of constraint. How many constraint equation that you have? X equal to 0. Sorry, I think y equal to 0, right? Yeah. Y equal to 0 is one equation. Z equal to 0 is second equation. So I have two equations. One equation is one constraint. So two equation means two holonomic constraints are there. So since both of them are holonomic constraint, okay, it is acceptable and we can proceed further. And remember that we are having two equations for the constraint C equal to 2. Okay, that is over. Then coming to the physical space, you always write 3D. This is very important. Physical space equal to 3D will not change from problem to problem. Any problem, whether it is 1D, even if the motion says one-dimensional harmonic oscillator, even then you write down 3D. Because oscillator is moving in the physical space. Physical space is always three-dimensional. That's all. You cannot say that I will write 1D for 1D problem. It's not like that. Even though oscillator is oscillating in one dimension, we will say that physical space is always 3D. So this is one important point. Okay, once that is clear, then what we will do is, we will now write down like this. The degrees of freedom before constraint and after constraint. That is the distinction that I am trying to explain. Now here remember one thing, that the degrees of freedom before constraint is always this 3. This 3 only you have to write here. And how do you write this is, for a single particle system. For one particle system, 3 means 3. For two particle system means 2 times 3. 3 particle system means 3 times 3. That's what you write down. And because we are talking about a single particle system, it is 1 multiplied by 3. So that is the 3 that you are going to write, and that is the maximum allowed number in the physical space. Okay. So that, because a single particle is very important. If it is 9 particles are there, 9 into 3 ought right. Okay, that is one calculation. And now comes the last calculation. The last calculation is degrees of freedom after applying the constraint. So of course, the statement I have already written, I will make it once again. So it's a very simple expression, degrees of freedom before constraint minus number of holonomic constraint. That's all. That's what you have to do. You already know that 3 is the, currently we have 3 here and we have 2 constraints are there. So 3 minus 2 is what you have to write down. And this is what we say final number of degrees of freedom. So remember that this calculation, this is what I said, that is last calculation, right? This is the last step. That is why I say final. Final degrees of freedom will be given by this expression. It is the degrees of freedom before constraint minus the number of equations available for us. Now in the present case, number of equation is 2 and maximum allowed is 3. So 3 minus 2, that's how you written, and so this is 1. This 1 is what is known as capital N. Now this is very important. Remember the symbol once again. I want to tell the symbol for that, capital N. This 1 is what is known as the capital N. So I'll write down. This means Q equal to Q1. Now this is the meaning. Meaning should be clear. Even though 1 and 1 are here, you cannot interchange N. So this N is single particle system. Single particle system means, okay, one particle is there, 1. Capital N equal to 1 means, what is the meaning of capital equal to 1 is, if you consider a mathematical space, okay, if you consider a mathematical space, dimensionality of the mathematical space will be equal to 1. That is the meaning that you are discussing. So now you see how the connection is. Physics you have. Physics means number of particles. That is physics. This capital N equal to 1 talks about mathematics. So you are making a connection. Now how the connection came is because of this calculation, the degrees of freedom calculation. So that means you are converting, or why do you want to convert? Of course, to understand. We want to understand the physical system. Since we are unable to understand the physical system directly by looking at that, you can't understand anything. That is what ultimately you have to understand. If a simple pendulum is oscillating, and ask the question why the pendulum is oscillating like that, why can't it oscillate in a different way? Like that, if you ask the question, there is no answer. You can't answer by looking at the pendulum for 1 hour. Even if you look at the pendulum for 1 year, you can't answer. So that is why you first of all try to translate. Translate means, translate. What are you translating is, a physical problem is equivalently translated in the language of mathematics. So when you are translating in the language of mathematics, we have a mathematical space for which dimensionality has to be calculated. So for this problem, dimensionality is 1. Okay, what is the meaning of that? The meaning is the set of Q's will be only Q1. Only Q1. Q2 is not there, Q3 is not there. So that is the meaning. And once this is clear, phase space is double of that. Phase space calculation is only double of this. So you simply multiply by 2 and you say that is the phase space. Okay, before closing this lecture, I'll give one more example so that you will be able to understand these numbers very clearly. Always talking about the single particle system is boring, right? So that's why I'm just showing. Forget about the single particle system. Let us have some multi-particle system, or we say systems of particles. We use the word systems of particles. Okay, this video is not fully visible. It's okay. Okay, so now it is visible. So now we are going to have 4 birds. You can count the number of birds here. So here it is there. So we are going to have multiple particles which are flying in a different direction. You don't even know what are the trajectories that you are going to have. So when you are going to have like this, for instance, okay, forget about this. So now in this example, what you are seeing is that instead of considering only a single bird, you are now considering multi-particle system. So that's what I am saying, that small n, which is the number of particle, because it is 1, it looks too simple. We can't have all the time 1 here. So let us consider another. That's why this example will be better, where we will not be having n equal to 1. So now the rest of the thing is clear. Okay, I think it's coming once again. Okay. So it is recorded multiple times. Okay, now it's coming. So what you understand from this is that how many number of birds were there? 4 of them are there. So you write down n equal to 4. Remember small n, because capital N is reserved for dimensionality of the mathematical space. Okay, fine. Then what did you understand? You understand that each particle is not constrained. So the birds are allowed to fly as it likes. So we don't have any constraint. So these things are different from the previous example, right? That's why I'm writing. Okay, so what you understand here is that we don't have any constraint, so there is no problem for you to search for the equation. So no constraints are there means c equal to 0. What is c equal to 0 is number of equation is 0. That is important. C equal to 0 means what? C means number of constraint. Equal to 0 means number of constraint equal to 0. So we don't have any equation for the constraint. That is the meaning. Okay. So after that, what you have to do? After that, we have to calculate the capital N. Now, as usual, remember that before going to the capital N, we should always start with the physical space. This is very important. Physical space means always 3D. But you have 4 particles. So therefore, 3 into 4. Okay, for 1 particle, you have 1 into 3. 2 particle, 2 into 3. 3 particle, 3 into 3. So right now, 4 particles are there. So you write down 4 into 3. So therefore, I will say that degrees of freedom before constraint is 12. And after that, you get the last. This is the last step. So degrees of freedom before constraint is 12. After constraint, what happens means you don't have any constraint equation. So minus 0, it will be 12. So our conclusion is this, that the degrees of freedom after the constraint is called final degrees of freedom. Remember, final. And what is another name for the final degrees of freedom? Final degrees of freedom is identically called the dimensionality of the configuration space. The terminology is important. Now that means, so what you understand is, again you have to understand what do you mean by that. The meaning is, let me therefore write down the meaning so that we can close today's lecture. The final conclusion is this. This means, I'll write down, this means Q means you have the set of Q12. So now you can understand how many dimensions that this n we used to tell, right? So now you have to stop exactly at 12. 11 also wrong, 13 also wrong. You can't stop at 11, even then it's wrong. Okay, I want one more Q13 can I keep means no, you are not supposed to keep. Then it is wrong. Only 12 only is allowed. So now you see that 12 is what is known as the degrees of freedom of the system. This is what the question paper will say, find out the degrees of freedom. Remember, degrees of freedom means final degree of freedom only. For your understanding, I used a different language, namely degrees of freedom. I remember what did I tell? I said that degrees of freedom, before constraint, after constraint, that is not the, the entire calculation steps, that is okay. But finally, degrees of freedom means always final only. That in between steps, generally, we are not interested. Only I am explaining for the purpose of doing the calculation. So remember once again, degrees of freedom means final degrees of freedom only. To achieve that final degrees of freedom, okay, you use the terminology before constraint and after constraint. That is the point to be noted. And now that degrees of freedom is equal to 12, and that is also nothing but the dimensionality of the configuration space. That is the final conclusion that you have. Okay, probably I think this is okay. This is not new here. What I am trying to do is, why only 4 particle? Why not you consider 10 particles or 20 particles? So then you don't have to repeat all the calculations. It's very simple. Of course, this is meaningfully c equal to 0. So now you see that 12 is there. Instead of 12, what to do? That is a question. The answer is that you write this n or this n. You can write this way or that way. Now you can understand, you see, I am writing 3 times n. You can understand how the 3 times n came. It is 3 times 4 only is 12. So what happens is, now why I am this explanation is that depends on the different books. Okay, in different books what happens is, some people will say, well, okay, Q3n. Some books will not say Q3n. They will say that Q capital N. So that is where the confusion comes. People will confuse why one book says 3n, other book says n. So it is not that whether you write 3n or n. Whatever be the case, Q12 is Q12 only. How do you want to write? That is, do you want to say that 12 equal to 3n? That is one way to write. Somebody will say that 12 equal to capital N. That's what I am saying. Capital N equal to 12. That is one way of writing. Somebody will say 3 times small n equal to 12. So these are the two ways in which people write in different books. So you should not get confused why 3 comes in one book, why 3 doesn't come, or any kind of confusion if you have. Now it will be clear. You can understand what is the meaning because of this one. Small n is there, capital N is there, number of constraint is there. And when you are generalizing to higher dimension, like I don't want 4, I want 40, n number if you have, then it is clear that we can always write down either in the green color notation or in this particular white color notation where Q3n comes into picture. Of course, remember there is one point is there that C equal to 0 here. If C is not equal to 0, of course minus C has to be written. So you understand that, right? Because C equal to 0, it becomes 12 minus 0, 12 came. Suppose C is 1, what will happen? If C equal to 1, then it is 12 minus 1. So I have to write 3n minus C. Similarly, capital N minus C. Now in our case, C is 0. So okay, so these are the things that I was trying to explain in today's class. And of course, I did not explain phase space, by the way. Yeah. So with that, I will stop. And only thing is that in the next class, I will consider the speed or the velocities and then bring that velocity also inside this, so that n dimensional become 2 times n dimensional. 2 times n dimensional. And many people say that it is even dimensional phase space. Even dimensional means what? 2 times you multiply anything, it is an even number, right? 2 times 7 is 14. So that's why phase space is always even dimensional. Whereas in the case of the configuration space, no need for that. Configuration space can be even dimensional, can be odd dimensional. Okay. For example, 12 minus 1, 12 minus 1, 11 is allowed. But 11 into 2, what happens? 22, right? Therefore, it is always even dimensional. So this point to remember, phase space means always even dimensional. Configuration space means both even is okay and odd is also allowed. Okay, so that point we will discuss in the next class.